Hey guys, this is Dave. Welcome back to the channel. If you're new here, I hope you enjoy the content, and by the end of the video, if you think I've earned your subscription, you'll consider hitting those like and subscribe buttons to come back and see more videos in the future. I tend to cover a lot of investing content, a lot of space stocks. One of my biggest companies that I follow right now is Rocket Lab, and I just cover all sorts of investing topics. We also have a new Discord server that I'm going to link down in the description below, where we hang out and talk investing, share ideas, and just try to work together to help grow our money. Today, I'm extremely excited to have a special collaboration video for you. I'm working with Unearthly Invest. If you're not familiar with his channel, I suggest you go check it out. I'll link that in the description as well. He covers a lot of the same stuff I do, focuses on space stocks, covering Rocket Lab, Astra, Relativity, all the big players you know and love. If you enjoy the type of videos I make, you'll probably enjoy his stuff as well. So check out the link in the description down below. Now, what we're doing today is we're covering the Electron versus Astra's newly announced Rocket 4.0. These two rockets are really going to be competing head-to-head for the same payloads, the same launches. There may be some differences in terms of orbits, depending on where they launch from and things of that nature. But really, these two rockets are going head-to-head, competing on the open markets for customers. So we thought it'd be a great time to do a comparison video between what I would consider the current king of the smaller launch vehicles, the Electron rocket, and the newcomer Rocket 4.0. Now, of course, Rocket 4.0 is still currently a paper rocket. It hasn't been built as of yet, but we know a lot about the plans that have been announced, and I just really wanted to see how these two rockets stack up together. How this is going to work is we're going to go over each rocket. I'll cover the Electron for each of these categories, and Unearthly will cover the Rocket 4.0 in those same categories, and we'll get a direct comparison on each, and then we'll wrap up at the end and give some thoughts. So, when it comes to size and lift capacity, the Electron can take 300 kilograms to low Earth orbit, 200 kilograms to sun-synchronous orbit. It has a diameter of 1.2 meters and a height of 18 meters. It also has a mass of 12.55 tons when fully fueled up, ready to launch. In terms of fairing size, the fairing has a length of 2.5 meters and a diameter of 1.2 meters. However, there is also an option for an extended fairing if you need a larger size to be accommodated. That extended fairing can have a diameter of 1.8 meters. Now, the Electron also has an optional kick stage spacecraft called the Photon. For rideshare missions requiring multiple deployments, as well as those requiring higher orbits, the kick stage can perform multiple burns to deliver spacecraft to individual unique orbits in a precise location. It was also used recently for the NASA Capstone mission to send small satellite to the moon, and is planned to be used to send satellites to Mars and Venus.
So Rocket 4.0 is a larger rocket than the previous Astra rocket. By how much, you ask? The current rocket Astra is using has a diameter of 1.32 meters or 52 inches and a height of 13.1 meter or 42 feet. In comparison, Rocket 4.0 has a diameter of 1.8 meters or 72 inches and a height of 19.4 meters or 64 feet. And the payload capacity reflects the larger dimensions of the rocket. While the current rockets have reportedly been able to lift only around 50 kilograms to sun-synchronous orbit, the new rocket should be able to lift 200 kilograms to the same orbit or 300 kilograms to LEO. This number is not coincidental. Chris Kemp said that the company estimated the average mass of satellites expected to launch over the next 10 years is 180 kilograms. And so Astra obviously aims to capture the majority of this demand with its new rocket.
The Electron is powered by Rocket Lab's Rutherford engine. It is designed and manufactured in-house by Rocket Lab. The Rutherford engine uses liquid oxygen and RP1, which is refined kerosene. It was originally qualified for flight back in 2016, and the first flight was in May of 2017. The engine is designed with the goal in mind of being simple and easy to produce. It is fabricated largely using 3D printing. The engine uses dual brushless DC electric motors and a lithium polymer battery. It is claimed that this improves efficiency from the 50% of a typical gas generator cycle to 95%. However, the battery pack increases the weight of the complete engine and presents an energy conversion issue. The biggest claim to fame from the Rutherford engine is that it is the first flight-ready engine to use this electric pump feed cycle. This means that fuel pumps are electrically powered by a battery, which differs from the traditional engine designs that divert some propellant to the drive pumps. With the Electron, all propellant is burned in the main chamber and a battery fuels the electric pump. The sea-level version produces 2.9 kilonewtons of thrust and has a specific impulse of 311 seconds, while the vacuum-optimized version produces 25.8 kilonewtons of thrust and has a specific impulse of 343 seconds. The Electron is powered by 9 engines in the first stage and 1 vacuum-optimized engine in the second stage.
Rocket 4.0 will use 2 engines that produce a combined 31,000 kg force of thrust, twice that of what the current 5 Delphin engines have been able to generate. The rocket will use 2 turbo pump-fed engines that will run on liquid oxygen and kerosene compared to the battery-powered pumps on the current Delphin engines. What is unclear to me at this point is how much will the Firefly deal help with the development of these particular new rocket engines after the deal was signed between the 2 companies. But given that the whole reason for purchasing the intellectual property from Firefly is to ultimately reach the goal of sending 500 kilograms to low Earth orbit, the Firefly's technology will obviously be critical in Astra's engine development moving forward.
Continuing on with the next category of cost, Rocket Lab tends to charge about $7.5 to $8 million per launch of the Electron. This can be divided up between several smaller satellites or just one larger satellite up to 300 kilograms in size. The addition of a special photon kick stage can take 130 kilograms to a sun-synchronous orbit, or 40 kilograms to interplanetary missions. We recently saw the Photon launch the capstone mission for NASA to the moon. That spacecraft is now well past the moon and continuing on its way, doing further tests. Photon pricing is not publicly available, largely due to many different configurations. But the capstone mission for NASA was $10 million in total, so if we subtract about $7.5 million for the Electron, just a rough estimate for this Photon vehicle would come out to about $2.5 million for that extra performance. There also is a future wildcard in the cost structure for Rocket Lab, as they are working towards and very close to making their Electron launch vehicle reusable for the first stage. About 50% of mission profiles would be eligible for reusability, potentially allowing them to lower prices further in the future or just increasing margins. The company has stated that reusability will allow them to launch at a much higher cadence and much cheaper than building a whole new rocket for every launch.
So as we said, the launch vehicle will be able to carry up to 300 kilograms into low Earth orbit at a base price of $3.95 million. To achieve these costs, Astra plans to use economies of scale. This is in contrast to how both SpaceX and Rocket Lab approach things with reusability.
The Electron is manufactured out of a lightweight carbon composite material. This is in contrast to aluminum, stainless steel, or titanium. In 2018, Rocket Lab unveiled a new production facility in New Zealand. The 75,000 square meter facility is designed for rapid mass production of the Electron rocket and complements their production facility in California. In 2019, they unveiled a new industrial robotics system called ROSI that can produce the carbon composite components of the Electron rocket in just 12 hours, a process that used to take more than 400 hours. The new robot is designed to complement the company's work in recovering and reusing the Electron first stages. When Rocket Lab announced in August its plans to attempt reuse of the first stage, it said that it was intended primarily to allow it to increase its launch rate faster than its vehicle production rate, with a goal of launching once per week. Even though we intend to recover Stage 1, obviously Stage 2, the fairing, and a lot of components still need to be built fresh from each flight, Peter Beck said. ROSI is really the enabler to try and get close to 7 days per launch.
In terms of manufacturing and the general Astra's approach to things, the company aims for simplicity. Astra's rockets are made with low-cost materials like aluminium and are using machine-casted parts versus 3D printed parts. The whole launch system can fit into a shipping container, and the automation aimed to decrease the number of people in the control room, as well as going from 5 smaller engines to just 2 larger engines in Rocket 4.0, obviously showed the general trend of Astra to simplify things. Astra's ambitious launch cadence requires equally ambitious manufacturing plans. The company's 250,000 square foot production facility reportedly gives the company the ability to manufacture 1 rocket every day. Astra hired a longtime Apple executive, Benjamin Lyon, as chief engineer to lead this manufacturing endeavor. This shows that Astra aims to achieve a manufacturing cadence never seen before in the rocket industry, and thus is ambitiously looking into expertise outside of the rocket industry altogether. The CEO Chris Kemp said he actually didn't want anyone from aerospace for that position, explaining that aerospace has not figured out how to build rockets at scale or do anything profitably ever. So I found no inspiration from anyone I talked to who had anything to do with any of the other space-related companies. If you look back at Apple and the things that Benjamin worked on there over many decades, he really took on not only designing the thing, but also designing the thing that makes the thing, which was more important than the thing itself. Astra wants to take Apple's approach to manufacturing, which is to work very closely with suppliers and move fundamental components engineering in-house. We can see that even in the fact that Astra didn't decide to purchase engines from Firefly, but rather the intellectual property, and then manufacture the engines in-house. And what Apple does is that it designs processes involved in making these fundamental components, and then have the suppliers build the factories to these exact specifications. And Astra's approach revolves around a similar idea and focuses on optimizing the output of its Alameda-based rocket factory.
On August 6 of 2019, Rocket Lab announced plans for the recovery and reuse of their Electron first stage booster. Due to the small size, Electron is unable to re-land propulsively, unlike the SpaceX Falcon 9. Instead, the first stage will deploy a parachute to slow it down in the atmosphere, and then it is caught in mid-air with a helicopter and subsequently returned to land. Initial inspections of recovered first stages that have re-entered the atmosphere have shown boosters to still be in good condition. Peter Beck, Rocket Lab CEO, is quoted as saying, "We were very, very pleased with the condition of the first booster we got back, with basically no modifications to any of the thermal protection systems." Beck continued that I think anybody who's not developing a reusable launch vehicle at this point in time is developing a dead-end product, because it's just so obvious that this is a fundamental approach that has to be baked in from day one of the design. Beck has advised that reusability will lead to large improvements in margins as well as launch cadence. In May of 2022, an Electron rocket launched 34 satellites to orbit. Then 15 minutes later, after deploying a parachute, the rocket was successfully caught in midair by a helicopter. This was the first attempted catch of a booster, and it was successful. After the catch, the pilot did not like the way the booster was flying while attached to the helicopter, and so he released it to splash down into the ocean. But Peter Beck has advised that they are extremely close now to making Electron reusable for about 50% of mission profiles.
While Astra said it remains open to the idea of reuse, they are not currently pursuing the idea, as their modeling and analysis suggested that this would only pay off somewhere in the range of 20 and 50 reuses. Both SpaceX and Rocket Lab are currently developing much larger rockets than what Rocket 4.0 aims to be, and so it makes a lot of sense that the two companies want to recover their costly vehicles. But as Astra aims to keep its launch vehicles small and cheap, it seems they ran the math and figured it does not make sense for them, at the very least at this point in time. And frankly, Astra has a lot on its plate right now, and a lot to prove and improve, even without diving into reusability. For that reason, it seems as the right decision to me not to delve into reusability before they can solve their bigger issues, such as being able to launch reliably, which should obviously be the top priority right now.
With the Electron launch on January 21st of 2018 from Rocket Lab's Launch Complex 1 in New Zealand, the launch complex became the first private spaceport to host a successful orbital launch. Launch Complex 1 features a 50-ton launch platform and tower, a hangar for the Electron rockets, and storage tanks for liquid oxygen and kerosene. On December 19th of 2019, Rocket Lab announced that they had begun construction on a second pad at LC-1 to be known as LC-1B to meet increased launch rates. It was used for the first time to launch on the mission The Owl's Night Continues for Cinespective on February 28th of 2022. With 2 launch pads and private range assets at Launch Complex 1, concurrent launch campaigns are now possible from the site. This enables resilient access to space by accommodating tailored customer requirements or late changes to a spacecraft while keeping Rocket Lab's manifest on schedule. Rocket Lab CEO Peter Beck has said that 2 pads could support 2 Electron launches within a day of one another. Launch Complex 2 is located in Wallops, Virginia. Rocket Lab's founder and chief executive Peter Beck says the completion of Launch Complex 2 in Virginia represents a new era in frequent, reliable, and responsive space access from the United States. Their Launch Complex 2 is tailored specifically for U.S. government missions to provide responsive launch for small satellites from U.S. soil. Between Launch Complex 2 in the United States and Launch Complex 1 in New Zealand, Rocket Lab can launch more than 130 times each year, offering small satellite customers unrivaled choice of orbital inclinations and control over their launch schedule.
The rocket will be a part of the company's Launch System 2.0, which is a mobile launch system that requires fewer people in mission control, with the aim to further decrease costs and be able to launch weekly. Initially, the number of people required for launch was 21, then 8, then 6, and ultimately they aim to have just 2 people in the mission control, similar to how you only need 2 pilots to fly people in planes. In terms of launch sites, Astra currently offers to launch its rockets from 2 US spaceports at Kodiak, Alaska and Cape Canaveral to a broad range of orbital inclinations, with plans to provide additional spaceports in the years to come. The so far announced destination for the next spaceport is at Saxaworth in the UK.
So, to wrap up, these two rockets have extremely similar capabilities. They're able to deliver the same mass to low Earth orbit as well as sun-synchronous orbit, but they get there in very different ways, and they have very different manufacturing techniques and launch infrastructure behind them. So, it'll really be interesting to follow the development of the Astra 4.0 and just track how these two rockets compete against each other. Obviously, Astra focusing on low manufacturing costs. They believe they can launch for about $5 million per launch, whereas Rocket Lab is more up in the 7.5 range, so they think they can really bring that price down. But on the other hand, Rocket Lab is getting very close to being able to reuse their Electron rocket first stage, which could lower the costs on their end as well. They haven't said if they would reduce their launch price in this scenario, but it seems like a realistic possibility. Of course, the Electron also has a long history of successful launches behind it, and Rocket 4.0 has yet to be built and launched. So things can definitely happen. Sometimes problems can be encountered or compromises have to be made. But on the other hand, improvements can be made too beyond the original design. For example, the Electron originally had a little bit less capability and it was improved upon and iterated upon. So Astra could potentially do the same thing there for Rocket 4.0 and actually improve upon their original design once they get it launching. As for which rocket is going to be more successful, I'll leave that to you to decide. What do you think? Does Astra's Rocket 4.0 have what it takes to dethrone the current king of the small-sat launchers, the Electron? Or does the Electron have the heritage and the reliability and the record to keep its throne? Let me know what you think down in the comments, and I'll see you guys next time. Bye.